In section 4.8, we are working with improper integrals. So an integral is an improper integral if either one or both of the limits of integration approach positive or negative infinity. So that is one type of improper integral that is typically easier to spot. But the second type of improper integral is when the integrand approaches positive or negative infinity on the interval of integration. So when we are working with this first type of integrals, what we're going to notice is that one of our limits of integration, or both, will be infinity, and we could think of that as unbounded. So we might have this question of how much area is there if I were to integrate, in this first example, 1 over x from 1 to infinity. So is there infinite area, or is there some specific amount of area? So we know that when we were learning about infinite series, that it is possible that we could have a region that adds up to a finite area, but that's only going to happen if our function gets to 0 fast enough. So our area could approach infinity, and if that happens, we're going to say that the integral diverges. So in other words, if the value of our integral approaches plus or minus infinity, the integral diverges. If the value of an integral approaches a real number, a real value, then we can say that that integral converges to that value. So we have to have a particular procedure. We cannot just apply the first fundamental theorem of calculus, the FTC, because when we read about the FTC, we know that it only works if a function is continuous on a closed interval. And so again, in this first example, when that limit is infinity, this is unbounded. Oops. Well, it would help if I could spell that. Unbounded. So it is not going to be a function. The function is going to be continuous, but this is not a closed interval. So that's our problem. So if we kind of imagine what's going on with this graph, if I think about the graph of 1 over x, I know from ouch 2 that in quadrant 1, my graph looks like this. In quadrant 3, the graph would look like this. I'm only really concerned with what's happening in quadrant 1 for this example. So if I imagine from x equals 1 to x equals infinity, I'd be calculating this area forever and ever and ever. And that's kind of hard to think about. So we have a special procedure that will allow us to manipulate what we're working with so that we can apply the FTC. So the first thing that we're going to do is we are going to assign a value a, and a is just some constant. So if I kind of erase some of my shading here, back up, let's say that I'm going to integrate, instead of from 1 to infinity, I'm going to integrate from 1 to a. So again, that's a value. So from 1 to a, I'm going to integrate 1 over x dx. But then I'm going to allow a to approach infinity. So I'm going to use a limit, and I'm going to limit this as a approaches infinity. So now we have a workaround. Now the integral from 1 to a is a definite integral, and it is a closed integral because a just represents some value of x that is greater than 1, at least in this particular example. And I can limit this so that a approaches infinity. So now we can use the fundamental theorem of calculus, whereas we couldn't when we just had an infinity. So when we go ahead and find our antiderivative, we really must, absolutely super important, write our limit notation and keep our limit notation. And if this ever comes up on a free response question, we absolutely must have our proper limit notation here. So when I take the antiderivative of 1 over x, I know that I'm going to get the natural log of the absolute value of x, and I'm going to integrate that from 1 to a. Now, in this particular example, we know a is a positive number, and we can just see on the graph that it's to the right of 1 on our number line. So we can actually drop the absolute value when we go to evaluate this. So using the fundamental theorem, we have found our antiderivative, natural log of absolute value of x. So I'm going to plug in my upper limit, so the natural log of a, and again, we're dropping the absolute value because we know a is positive, minus the natural log of 1. And of course, we know that the natural log of 1 is 0. So when we think about what's happening as we fill in infinity, like as we allow a to approach infinity, really, this is just the natural log of infinity minus 0. And we know that natural log is going to go to infinity. So this is going to blow up. We are going to get infinity. So this integral diverges. This integral diverges because the area is going to approach infinity. Like it's going to be infinitely more area the more we go. But it's kind of counterintuitive because that just doesn't always happen. So let's look at our second example. All right, so we're going to do the same procedure here. We have now our integrand is the function 1 over x squared. So I'm going to, again, integrate this from 1 to a. You could use really any constant you want there. I'm going to call it a, call it b if you want. My integrand is x squared. And we're going to limit this again so that a approaches infinity. So now I notice that my integrand isn't 1 over x, it's 1 over x squared, which is the same as x to the negative 2 power. Sometimes it helps me to just write that out to the side. So when I go ahead to find my antiderivative, don't drop our limit notation though, I'm going to use the power rule. So I'm going to add 1 to my exponent and divide by my new exponent. And this is what I'm going to evaluate at my limits. And you know me, I have to rewrite it because that's hard to think about. So this becomes negative 1 over x, and we're going to evaluate that from 1 to a. All right, so again, our limit as a approaches infinity, I'm limiting negative 1 over a minus negative 1 over 1. So I could really think of that as the limit as a approaches infinity of negative 1 over a plus positive 1. So now when I plug in infinity, negative 1 divided by infinity, when my denominator is approaching infinity, that's basically 0. Like I'm dividing a negative 1 by a number that is so large that negative 1 over infinity is 0. So the value of this limit is just 1 because it's like I'm adding 0 plus 1. So we could say that this integral converges to 1. So there's a theorem that anytime we have our integrand where we have x to a power, if I have x to a power, if my power is greater than 1, then my integral converges. If my power is less than or equal to 1, my integral diverges. Now, there's a couple of notes here. This is going to be true anytime that we are integrating a positive constant to infinity. So this is only true when we're integrating a positive constant to infinity. So what I mean is that 1 there, that could really be any positive constant. It could be a 2. It could be a 7. And again, notice that infinity is our upper limit here. If we look at 2 more examples that do not, like we cannot apply this theorem because it is not x to a power. Well, let's try this first one. In fact, you might want to pause the video and try the first one for yourself. All right, so I'm going to integrate from 1 to a e to the negative x dx. And again, I must limit this so that a approaches infinity. So when I think about e to the negative x, I think, is that one of the rules that I know? And the answer is not really, because of that negative x. So remember, this is when we do a u sub. So if u is a negative x, our du is just -1 dx. So you may or may not have to actually write out the whole u sub. We can often just hold our thinking, but basically I need a negative for my du, so that means I need a negative out front. All right, so now when we go to our next step, again, it's our limit as a approaches infinity. Now I'm going to go ahead and integrate that. I just have e to the u du in my integral. So I know that the antiderivative of that would just be e to the u plus c if it wasn't a definite integral. But remember, we had to put that negative out front. So we're going to get negative e to the negative x. So that's negative e to the u. And we're going to evaluate that from 1 to a. All right, so again, our limit as a approaches infinity of, well, when I go ahead and plug that in, I get negative e to the negative a minus negative e to the -1. And of course, I'm going to want to rewrite that so that I don't make a mistake as -1 over e to the power of a. So I'm going to get rid of my negative exponents. And then instead of subtracting a negative, how about plus 1 over e to the power of 1? So now, if I think about a approaching infinity, that first term, -1 over e to the a, well, the denominator is going to blow up. So that's going to become 0. So I'm basically adding 0 plus 1 over e, which is just 1 over e. So again, for this integral, it converges to 1 over e. All right, for the last example, there are 2 ways to do it. One way that I think can feel harder. So if we imagine that we're going to integrate 1 over x squared plus 1, but we notice that both of our limits of integration are infinity. Well, one is negative infinity, one is positive. So if I think about the graph of 1 over x squared plus 1, I know when x is 0, it's at a maximum of 1 there, and it's going to kind of curve off like that. So what we could do is we could split this up at x equals 0, and because this graph has symmetry, like we could integrate from 0 to infinity, just like we've been doing before, and then if we get a value, we could double it. So that is one way to do it, because when we double it, we'd be getting the area from the other side. But there's another way that we could do this that might be easier, and that is that we could actually give an a and a b here. So instead of having limits at negative infinity and infinity, I could say that A is going to be some negative constant way out on the left of my graph, and B is going to be some positive constant way out on the right. So we will limit this integral. So our limits will be A to B. You know what? I think I actually need a little more space there. Sorry. But not only do we need to let A approach negative infinity, because A is on the left, at least the way that I'm writing this, but we also need to let B approach positive infinity, because we want to scooch that B all the way to the right forever and ever on our graph. All right, well, this might look a little more complicated, but it's a lot like what we've been doing. So we'll go ahead and find our antiderivative, and we recognize that that is our arctan antiderivative. So we're going to have the limit as B approaches infinity and as A approaches negative infinity of arctan of x, and we're going to evaluate that from A to B. When I say from A to B, we plug in B first, though, using the FTC. All right, so let's go ahead and use the FTC. We're going to get so good at our limit notation since we get to practice it so often. All right, so applying the fundamental theorem, we get the arctangent of B minus the arctangent of A. And now I've got to think about what's happening to arctangent as B goes to positive infinity and A goes to negative infinity. And in order to imagine this, we need to either know what the graph of arctan looks like, or we need to remember something about inverse functions and know what the graph of tangent looks like. So if we go ahead and graph y equals the tangent of x. Well, I know that anytime cosine is 0, tangent of x is going to be undefined, because think of tangent as sine divided by cosine. So I'm going to think of this as happening at pi over 2 and at negative pi over 2. And then if I remember from trig or honors algebra 2 what this tangent graph looks like, there's going to be vertical asymptotes at negative and positive pi over 2. And we also know that this graph repeats. We're really just looking at one period of this function. So if we consider arctan now, if I want to think about the graph of arctan of x, remember that's the inverse of the graph of tangent of x. And something we remember about inverses is their x's and y's swap, essentially. So I could think of like the domain and range of one function is the range and domain of the other. So like your domain and range swap when we think of inverses. And also things like, in this case, vertical asymptotes on our tangent function will become horizontal asymptotes on our inverse function. So I know that the graph of arctangent of x is going to have a horizontal asymptote at positive pi over 2 and also at negative pi over 2. All right, so that's what our graph of arctangent of x will look like. So if I go back to what I'm evaluating, as B approaches infinity, so B is approaching positive infinity, arctangent of B is going to be pi over 2. because this graph is headed to this horizontal asymptote of pi over 2. So when I go to evaluate this limit, oops, I was trying to write that in the same color. When I go to evaluate this limit, the arctangent of b as b goes to infinity is pi over 2. And then I want to think about the arctangent of a as a goes to negative infinity. Well, on the graph, if I go out to negative infinity, I'm approaching this horizontal asymptote at negative pi over 2. So I'm subtracting the arctangent of basically negative infinity, which is negative pi over 2. So that becomes pi over 2 plus pi over 2, which of course is 2 pi over 2, or just pi. So in these first few examples, we worked through some improper integrals, and we said some of these converge, some of these diverge. This last one converged to pi. And we said that these are easy to spot because I can see my limit of integration is either positive or negative infinity, or that happens twice.